Hi, everyone. Welcome to Neurolective's webinar. My name is Rafał Nowak, and I will be your host today. And today, we'll be talking about important topic with the motor hotspot localization based on the EEG using convolutional neural network. And I'm very happy to welcome our guest speaker. And today we have with us Dr. Choi. Hi there, Gayong.
Hi, nice to meet you.
Please let me quickly introduce our speaker. Dr. Choi is the distinguished postdoctoral researcher in the Department of Bioengineering at McGill University in Canada. He has a rich academic and research background, holding a PhD in electronics and information engineering from Korea University, South Korea. Her academic journey includes significant contributions as a postdoctoral researcher at Korea University Smart City Intelligence Healthcare Research Center and as a visiting researcher at the Technical University of Berlin in Germany. Dr. Choi's research interests are centered around computational biomedical signal analysis, machine learning, deep learning algorithms, but also neuromodulation and rehabilitation using non-invasive brain stimulation, human-computer interactions based on techniques like EEG and FNIRS, also biometrics based on EEG and ECG. And Dr. Choi also holds several patents in the field of neurotechnology and biomedical engineering, highlighting her innovative contributions to the development of advanced diagnostic and therapeutic tools. So welcome, Dr. Choi. The stage is yours. You're ready to present. And thank you very much for joining us today.
Thank you. First of all, thank you for introducing me. And hi again, I'm Choi. I majored biomedical engineering, specifically, actually already mentioned, I try to interpret the biosignals, such as electroencephalography, electrocardiography, myography, and even the bold signals like fMRI, NIRS, and so on, and developed various healthcare applications based on those kind of signals using machine learning techniques, including the AI techniques. So based on those knowledge, today I would like to talk about our proposed deep learning algorithm to automatically identify the optimal brain stimulation site for effective neurorehabilitation. According to the World Health Organization, WHO, reported the death rate related to stroke reached 6.6 million in 2019, making it the ranking third as a cause of death worldwide. It is a major social problem that causes a serious motor dysfunction, impacting the quality of their life for both patients and caregiver, like a family and their friends, and potentially leading to the chronic health issues. Therefore, understanding these challenges and developing effective rehabilitation programs are crucial. So one of the efficient neurorehabilitation method is a transcranial electrical stimulation, TES, which is a non-invasive brain stimulation technique to modulate neural excitability by applying a minute current around 0.5 to 2 milliampere to the scalp. It can be broadly divided into three types, depending on the applied current types as TDCS, TACS, and TRNS. Evidence from lots of studies supports the important role of TES in improving motor functions after stroke or any other cerebral disease, Parkinson's, and so on, particularly in enhancing hand movement skills. As you well know, the standard TES typically comprised a single anode and cathode electrode. To enhance hand motor function, the anode electrode is positioned on the primary motor cortex, as called M1 site usually, in the contralateral hemisphere of the paralyzed hand, whereas the cathode electrode is positioned either on the ipsilateral M1 site or supraorbital region of the same hand. In more detail, as shown in this figure, based on many previous studies, TES electrodes are commonly placed at the C3 and C4 location based on the International 1020 system, or the motor hotspot for enhancing the hand motor function. First of all, the position of the C3, C4 typically refers to the electrode located anatomically near the primary motor cortex, especially the hand knob areas, which is anatomically governing our hand movements. By the way, the motor hotspot refers to the specific motor area functionally governing the hand movement. It is typically located anterior or posterior related to the hand knob area as looked like here, and its location varies among individuals. Moreover, the recent study based on the transcranial magnetic stimulation have demonstrated the importance of precise stimulating to individual motor hotspot than the hand knob area. To find the motor hotspot, as shown in this figure, a device called TMS is used to apply a single pulse to the scalp to evoke the component of motor evoked potential. To observe the MEP, a separate EMG sensor must be attached to the target muscle. For example, the first dorsal interosseous FDI muscle is commonly targeted when assessing hand motor function. Then the technician tested several points on the scalp with the primary motor cortex and finally defined the motor hotspot site where the MEP is most prominent. However, as I explained above, the conventional TMS based on the hotspot identification method involves a considerably complex process and also required the empirical judgment of experts to determine the hotspot location based on the evoked MEPs. In addition, as you can see here, the TMS equipment is quite bulky and expensive. So to do this, the patients with limited mobility have to visit the hospital frequently. We think that this issue can be a factor that diminishes the compliance and effectiveness of the treatment. Therefore, considering that the TES and EEG integrated equipment has already been commercialized, our research team has proposed an automated motor hotspot identification algorithm using EEG data that can be measured relatively simply without requiring expertise. Moreover, we validated the clinical feasibility by applying our novel motor hotspot identification method to EEG from the actual stroke patients. Considering to the distinguishable differences in EEG patterns between the stroke patients and healthy controls. At first, we investigated the possibility of individual motor hotspot identification using EEGs. This feasibility study was conducted 30 healthy participants. Before conducting EEG measurements, we identified the motor hotspots in both hands for each subject by analyzing the TMS-induced MEPs of the FDI muscle. So we used the single pulse TMS on the contralateral motor cortex to find their motor hotspot. To record the location of the motor hotspots, we used a digitizer to mark the 3D coordinates based on the vertex, in other words, the location of the CZ point in terms of the International 1020 system. The coordinates serves as the ground truth for comparing with the estimated obtained through our EEG-based approach. For each recording, 63 EEG electrodes were placed on the scalp according to the 1020 system to measure the EEG data, and the data were measured a sampling rate of 10,000 hertz. The subject performed a simple finger tapping task to collect movement-related EEG data. They were instructed to press the spacebar with their index finger whenever a LED circle appeared on the center of the monitor. Each trial involving a hand movement task followed by the relaxation period of 3 to 7 seconds randomly was performed 30 times for each hand with sufficient break time to prevent excessive fatigue. In other words, each measurement were separately conducted for index finger of left and right hands respectively. The low data were first downsampled into 200 Hz to reduce the computation load, to which we subsequently applied common average reference for the referencing and bandpass filtering between 0.5 to 50.5 Hz. And then independent component analysis was applied to the filter the EEG data, remove the physiological artifacts. After that, we excluded the EEG data significantly contaminated even after applying ICA by visual inspection. Consequently, the EEG data of one subject for both hands and those of left hand for other 3 subjects were excluded. After pre-processing, we epoch the EEG data between minus 0.5 and 0.5 seconds based on the key press point for each trial to extract motor-related EEG features. For the features, the power spectral densities of each EEG epoch were estimated in 6 frequency bands, especially delta, theta, alpha, beta, gamma, and full frequency bands using the fast Fourier transform method. And then an artificial neural network model, as it looked like here, was used to estimate the motor hotspot location using the PSD features, where a 10-fold cross-validation was performed with early stopping to prevent overfitting. Among 10-fold, the 9-fold of PSD features of each channel were used as training data with the 3D coordinate of the motor hotspot identified TMS approach as labels. Then the left 1/4 of PSD features were then fed into the trained ANN model as the test data set. And finally, the ANN model output the XYZ 3D coordinates of the motor hotspots predicted by EEGs. We calculated the Euclidean distance between the 3D motor hotspot coordinates identified by TMS and EEG PSD features to quantitatively estimate the error distance of our EEG-based motor hotspot identification approach. The data analysis was independently performed for each of the 6 EEG frequency bands to investigate the optimal features. Furthermore, we also investigated the impact of the number of channels on the error distance. We repeatedly performed the dimension analysis by gradually reducing the number of channels, in particular focusing on the channels attached to the motor area. Note that channels denoted by different color in channel set 4 here, you can see the different color noted according to the hemispheres. So in channel set 4 represents those selected on the contralateral motor cortex for data analysis for each hand. As the result, this figure shows the grand averages event-related potential measured during the finger tapping task between -0.2 to the -5 and 0.5 second by averaging the movement-related ERPs, actually the movement-related cortical potential of 4 channels located on each hemisphere of the motor cortex. Our data shows the clear MRCP patterns on the motor cortex during finger tapping task for both hands, and especially strong MRCP pattern was observed in the contralateral motor area. In case of the left hemisphere, the left line, actually the right hand movement shows more stronger MRCP patterns, whereas in case of the right hemisphere, the left hand's condition shows a more strong patterns. So it demonstrating the reliability of our EEG data by showing the general patterns. And this result shows the mean error distance of the motor hotspot locations as estimated by our EEG-based machine learning approach for each hand, right and left, with respect to the frequency band when using all 63 channels. The PSD feature of the relatively high frequency bands, the beta, gamma, and full frequency bands result in significantly lower error distance than those of the low frequency bands, delta, theta, alpha for both hands. Especially the gamma frequency bands shows the best performance of 0.22 centimeter. So we only used the gamma PSD features for further analysis. It presents the mean error distances of motor hotspot locations estimated by our approach with respect to the number of channels. In general, the mean error distance increases monotonically or significantly as the number of channels decreased, but it remains below 1 centimeter up to the channel set 4 condition. So at the first study, we proposed a novel EEG-based motor hotspot identification method using an artificial neural network model as a potential alternative to TMS to determine TES target location for motor rehabilitation. Especially, it was documented that reliable FDR muscles MEP was observed with an area of approximately 12.9 square centimeter, meaning that a reliable MEP could be evoked with a distance of up to approximately 1.8 centimeter based on the center of the motor hotspot area. And moreover, considering that the commercial TS electrode size is typically more than 1 centimeter, we expect that the error distance of the motor hotspot identified by EEG PSD features is sufficiently acceptable. Although we have confirmed the feasibility of our approach, EEG-based approach, the EEG pattern of stroke patients can vary depending on the location of the region and its severity. As demonstrated in this study, there are notable differences in EEG patterns between healthy individuals and stroke patients. Furthermore, in this figure, the EEG patterns can vary within even the same stroke group based on duration of disease onset and its severity. So in this follow-up study, we proposed an advanced EEG-based motor hotspot identification algorithm using deep learning techniques that can reflect the individual characteristics for stroke patients. In this study, we used the data from 29 healthy control and 29 stroke patients. The Novel proposed deep learning-based algorithm was first verified using healthy individuals' data, and then its clinical feasibility was verified by applying the actual patient's EEGs. We used the data from the same healthy control group as we used in previous study, and the stroke patients also collected through the same protocol as the healthy groups. By the way, due to the limited motor ability in stroke patients, the finger tapping task was replaced with simple hand grasp task, where the patients lightly grab their hand whenever the LED circle appeared on the center of the monitor. The pre-processing applied almost the same procedure to that in previous studies. So we're gonna sequentially apply the resampling, rereferencing, bandpass filtering, and ICA for artifact rejection. And exceptionally, the data were segmented between minus 0.5 and 1 second based on the visual stimulation, indicating the starting point of the task for each trial, especially for the stroke groups, because we accommodated some variation in task completion times between patients because of their severity, but all subjects were completed within 1 second, so we evoked this period for the stroke patients. Additionally, we divided the input data into 5 types to evaluate the impact of different levels of signal processing on the performance of the proposed deep learning model. So we tested 5 different types of input values, each progressively refined it from previous stage. For example, in case of input 5, this input is exactly same as in previous study. We applied common average reference, bandpass filtering, ICA, and extracted the gamma extracted the power spectral density of gamma frequency bands as features using FFT, as it was identified as the optimal feature in our previous result. And in case of the input 4, we only applied the pre-processing from CAR to ICA without the feature extraction steps. So it means we just using the time series data as the input of the models. For in case input, we remove the ICA steps and only apply simple pre-processing. And finally, for input 1, only epochs were included and time series data without any other pre-processing was used as the inputs. And then after then, this two-dimensional convolutional neural network model was used in this study. It was trained and tested using trial-wise based nested cross-validation approach to build a user-adapted model that accounts for individual differences. The data from each subject were independently used for the model training. And the error distance was quantitatively estimated by calculating the Euclidean distance between the 3D coordinates of the motor hotspot identified by TMS and those determined by the EEG-based deep learning approach, as the same with the previous study. Additionally, we investigated the impact of the number of channels performed of the motor hotspot identification. Honestly, we used the other EEG equipment for stroke patients data collecting. So there is only 29 EEG electrodes. So we just reduced the number of channels. Looks like this. So the channel reduction, how can I say, the number of channel, the type of channel reductions are a little bit different between normal condition and stroke patients. This result presented the mean error distances of the motor hotspot location estimated by the EEG-based deep learning approach, depending on each EEG processing level using 63 channels. It means the healthy controls data. The error distance gradually increased as the feature engineering reduced, but even though the input of low data, in case of the input 1, showed the largest mean error distance of 2.22 millimeters. This error distance is still practically usable considering that the diameter of the commercial TES electrode size. Given that the error distance of the motor hotspot identified by input 1, the low data, was acceptable in practicality, so the low data was utilized for subsequent analysis. And it shows the mean error distances for both hands with respect to the number of channels using low data. It shows that the mean error distance of less than 3 millimeter under all conditions. Notably, the average error distance was 2.34 millimeter, even when only using 9 channels around the motor area. Especially the current study demonstrates significantly superior performance compared to the previous study that reported error distance of 10.3 millimeter. It means around 1 centimeter under the same condition. Finally, we validate the clinical feasibility using actual stroke data. As a result, despite the different neurological patterns observed in the EEGs of stroke patients compared to those of healthy individuals, all channels that showed a mean error distance of approximately 2 millimeters. In particular, the error distance was only 1.77 millimeter when using only 5 channels around the motor area, and there are no significant differences between the pedalized or non-pedalized hand condition. In this study, we proposed an advanced EEG-based motor hotspot identification algorithm using deep learning technique, aiming at replacing the conventional motor hotspot identification method that uses TMS. Consequently, it demonstrates a substantial improvement in accuracy by approximately 82%. Most importantly, the best mean error distance of stroke patients was 1.7 millimeter, which could be clinically feasible considering that the diameter of a commercial TES electrode size. On the side, this additional result shows the change of mean error distances according to the number of trials based on the minimum channel. It means only using 9 channels of low data in healthy control. It shows the robust performance in terms of the number of trials, and acceptable mean error distances was maintained even when the number of trials was reduced by third. However, the mean error distance linearly increased as the number of trials was reduced, reaching around 5 centimeter when using only 5 trials for model training. To effectively utilize our proposed algorithm in clinical setting, using a minimal number of trials is advantageous for training the model since they are obtained from the patients with motor impairments. Therefore, we plan to enhance the robustness of our proposed model in terms of the number of trials in future study. In conclusion, this study, a novel EEG-based neurorehabilitation approach was proposed to automatically identify the individual motor hotspot using machine learning and deep learning approach as an alternative to TMS approach, and demonstrated its feasibility via EEG experiments. And also we verified clinical benefits based on EEG data from actual stroke patients. Based on this result, the integration of our developed algorithm into commercialized portable TES EEG devices facilitates the automatic and precise identification of motor hotspots, enabling the simultaneous application of TES without the need of the TMS-based manual procedure of identifying motor hotspots. In this respect, our proposed approach for identifying hotspots is anticipated to advance home-based motor rehabilitation through the application of the TES techniques, improving accessibility and usability for individuals' limited mobility, thereby reducing the necessity for frequent hospital visits. From that, we expect that improving patients' compliance and participation in rehabilitation would be enhanced neurorehabilitation outcomes. In closing, I want to acknowledge and introduce our amazing team members who contributed in this work. We have applied for an international patent based on this result, and we are actively conducting various brain stimulation studies, other studies. So if you have any further questions or feedback, please feel free to contact us. We are truly welcome your continued interest and support. And lastly, I would like to thank you for the neuroelectronics, especially today's host, Leffer, Losa, and Sarba, for giving me this opportunity to address such a distinguished audience, and also for every audience, your patience and interest are greatly appreciated. Thank you.
Thank you very much. Really interesting presentation and the solution that you provide to the patients and actually to the clinicians and the researchers. So we have time for a few questions. If you have any questions, and I'm talking to our audience, please use Q&A tool in Zoom. But before we start with the questions from the audience, I have like the simple questions actually. So if you can summarize, how many channels of EEG would we need to get a reliable localization of the motor hotspot in terms of normal subjects and in strokes? What would be the minimal number?
The minimal number is based on our result. It is 5 channels around the motor cortex, because you can see here, it shows around 2 millimeters error distance, even we use the 5 channels around the motor cortex.
Okay, and in this sense, this will be for a motor cortex in the left hemisphere and on the right hemisphere, but you still have to use all 5 channels.
Sorry again.
So these 5 channels will be enough to get the localization on both left and right motor cortex.
Yes, it's true, because we just attach it like here around the center area, the 5 channels, and we estimated for the right hand, left hand, their average error distance is around 1.7 millimeters. So just 5 channel is enough for estimating both hemispheres hotspot.
It looks amazing, and especially from the practical point of view, and where you can use only these few channels. And I could see actually a lot of application for the improvement of BCI for motor imagery. BCI, for example, actually to locate exactly the electrodes in the place where is the motor hotspot with the perfect localization. Do you have any experiments with the motor imagery BCI using this kind of approach, or do you plan to do any studies with the motor imagery?
That's really good questions. And actually, I'm considering about that because some stroke patients can't their hands easily. So some people is really hard to just hand grasp. So I considering using the motor imagery task also, but I don't have the result yet. So someday, if I got a result, I can sharing with you.
Okay. And what is your opinion regarding localization of other primary sensory motor areas or even secondary areas like language area or the cognitive secondary area using this approach?
Yes, that also really good points. And also we are considering about that because the TES can be used for the cognitive or the other psychiatric disease. In this case, we have to target the other area like DFFC, something like that. So I in my opinion, if we find the optimal paradigm to define the specific area for the kinds of cognitive or psychiatrics, we can using this algorithm for the cognitive also. But we have to test it in using the real data. So that is also our future plan, one of our future plan.
Okay, okay, and especially using the correct task, I guess, because if you are using a finger tapping, so for motor cortex, let's say that this is quite easy. When you
Yeah.
are getting to the cognitive functions, that the whole problem is getting more complex, and you have to use
Yeah, I
the
hope.
correct task actually to evoke the activity that you are interested in. Okay,
Mhm.
and the question, like from the more technical point of view, so you are using the deep learning models and particularly the convolutional neural networks.
Yes.
So what are the advantages of like more traditional machine learning methods? What would be the advantages of using CNN comparing to
Yes.
more traditional machine learning methods?
Yes, our advantage is when we're using the deep learning approach. Actually, in terms of the result, we can see the more higher performance when using the deep learnings. And also, we can using just the low data without any other pre-processing steps. It means it doesn't need the expert know-how. Let's considering about the real rehabilitation environment. If we using this algorithm and the TSEG integrated system, the participants just put on the devices on their head, just performing the simple finger tapping task, they can find the hotspot automatically without any other processing or expert know-how, and they can get the rehabilitation in their home. This is advantages than the traditional machine learning because of, as you know, aware the machine learning need to the professional pre-processing step is required. So that is the biggest advantages for using the deep learning.
Perfect, perfect. Thank you very much. And in terms of actually, yeah, because you are applying this specifically for stroke patients. So if you are taking into account the severity of the lesions in stroke, how you plan actually to include in the model differences between normal subject, between stroke, and then the different variability in stroke lesions and severity. So do you plan to like any specific adaptation to ensure accurate hotspot identification in different severity of patients?
Oh, yes.
Yeah.
In this study, we just using the acute stroke groups, but
Okay.
we can gathering the other severity groups of stroke patients. And then I hope someday we to try to testing the other severity groups, also more light and more severe groups. And we have to testing the changes, the performance. And in this case, we suggested the individual adapted model. I think if there are more severe or more lighter, it could be it doesn't matter because it is user adapted. I think the model can be adapted their severity also. So, but I have to test it.
Perfect. Perfect. Thank you very much. So this was the last question. Thanks for the presentations. Thanks everyone for joining us today. And I hope you will join us again for the next webinar. So please visit our webpage, neuroscience.com, where you'll find more information about the upcoming webinars. Thank you, Dr. Choi, for joining us today. It was a pleasure. Thank you very much. And have a great day. And see you again in the next webinar. Take care.
Thank you so much. Have a great day.
Thank you. Goodbye.